All right, recording is rolling. Welcome to Tuesday, August 29. All right, so for video context, we are about 10 minutes into class. I've given you guys the first 10 minutes about to score your AP style write-up for the car and incline lab using these rubrics. There's 4 different rubrics, so I got these passed around. You guys are doing that. I'm having you guys turn in 3 parts to this lab. I'm looking for your guys' lab table, the 6 graphs that we put together back on Friday, and also your AP style write-up that you guys are doing. And score yourselves with that colored pencil. Your score, because I want you guys to follow the rubric and see. I tried to make rubrics that were really close to what I thought AP would look for. However you score yourself, I made an extra column in the grade book that doesn't count towards your class grade. So if you score like 5 out of 12 or 2 out of 12 or 10 out of 12, that doesn't affect your class grade. It will be there so you can see it, but it's just way zero. All right, so you can keep track as the year's going on. All right, so there you go. That's the lab. You guys get a chance to turn that to the grade tray, and I will give you guys credit just for doing that. As long as you have those 3 parts, then you'll be good to go in terms of your class grade. All right, so I got a 3-part starter question here. Let's take a look at this real fast. Suppose you're at the edge of a cliff. So this is really fundamental constant acceleration, linear motion physics. Right, we're going to drop a ball from the edge of a cliff. Here's my 3-part question. Part 1, how fast is it traveling after falling for 3 seconds? Part 2, how far did it fall during that same time interval, during 3 seconds? Right. And the third question is, suppose the cliff height is total 80 meters tall. Right. In that case, how fast is it going to be crash landing on the ground? Right. By the way, I picked those 3 questions because each one of those involves one of 3 different kinematic equations. Right. I want to get you guys started on linear motion puzzles today. Okay, we may or may not have school tomorrow. I don't know, it's a coin toss, but hopefully I'll get you guys a good spot where if you got some extra time tomorrow, you be in a good spot to start some of those. All right, I have some tentative due dates. So here's what we got in terms of what's due around the corner. Now these linear motion puzzles, I'm just going to make this like an extra credit type assignment. If you do these and turn them in and it all looks good, then I'll throw some extra points in the book for you. Right. But you guys have this college physics. This is really what it's like at your guys' level. It's college physics. You guys see how I circled some of these? Like I circled number 20 on the front, and I circled a bunch on the back. Right. I think there's 10 problems that I circled. I think that's pretty minimal for like an AP college level class, but do those for sure. If you do those, then it's complete. If you want some extra ones, there's some that I've starred that I would like to go over in class. Again, like time's always an issue, but right. And then if you even want some more, then I've got lots of extra problems on here too. Right. But the ones that you guys are going to turn in, then I'm going to give you guys credit for are the circle ones. If you do all the ones that are circled, okay, you guys got that? Okay. All right. So tentative due date is Tuesday the 5th. That's coming back from 3-day Labor Day weekend. All right. And then AP Classroom's been open for a while. The tentative due date there is Thursday the 7th. If I have to push that back, that's possible. I don't know, but for now, that's what I got lined up. Okay. All right. So you guys good with what's going on here? All right. So let's tackle these 3 questions. We're at the edge of a cliff. We're gonna drop a ball. Ooh. Here, okay. Let's jump to the first one. How fast is it moving after 3 seconds? How fast after 3 seconds? Okay. Who knows how fast? Wait, Kevin. 30 meters per second? How'd you know it was 30 meters per second? Yeah, acceleration times time, right? In fact, you know one thing, an additional thing that's probably so intuitive to you that you just, right here. What is the drop? What does the word dropped mean? What does that tell you physically? Initial velocity is what? 0 meters per second. All right, which can help you out too. And then after that, it's exactly what Gavin said. Here, is it this one right here? Because I asked how fast is it going after falling for some time, and a gravity field is like an accelerating environment, right? Is it? So we're going to write this down on paper. Right. So we're just using this second kinematic formula right here. Final velocity is initial velocity plus acceleration times time. If you like, you can make this a lowercase g because it's a gravity field, right? That's common to do, right? Okay. Yeah, Paul Hewitt did that, right? Good call. Right? Oh, initial velocity is 0 meters per second. You guys just said because you dropped the ball. Right? It's implied that you're on. I didn't even write Earth, and you guys are thinking, oh well, it's probably Earth, which is a good call too. Right? So the speed it picks up to after 3 seconds says, well, we're doing 10 meters per second squared times 3 seconds. And one of these seconds cancels with that seconds, gives you meters per second. Boom, 30 meters per second, just like that. You guys can do that? You guys can do that? Right? Right, all good? Right. You guys ready for the next question? Right. All right, you guys are 1 for 1. Let's see if you guys are gonna get this next one. How far does it fall in 3 seconds? Which they, Gavin? 45 meters. All right. Oh, Gavin's 2 for 2. How'd you know it was 45 meters? How'd you know it was 45 meters? Did you use some version of this right here? All right. In fact, you know what? Can we make the same simplification we did in the last one? The fact that initial velocity is 0 meters per second, can we just drop that out? So the fact that you drop the ball, what happens to this term right here? Just goes to 0, right? Right? So we can more simply say how far it falls, like x could be in meters, right, is equal to, I'm just going to let this term go to 0, right, because it starts from rest, right? I got 1/2, maybe A, I'll call it G again, because gravity field, 1/2 GT squared. Hey, you guys have seen that at least a couple of times in the last week. What Polyhewitt story was this? Ah, yeah, right. Remember? Oh, there's an old mine shaft. Dusty, dank, or dark, dank. Hear the bats. College. You guys remember college? That's the college equation. That's it. So let's do what Gavin did here. We got 1/2. We got 10 meters per second squared for the gravity field because we're on Earth, right? Some of you guys might say 9.8. That's okay too. AP will accept either. Right? And we're doing 3 seconds. Square the time. All right, guys, does that square apply to the 1/2 and the G and the T, or just the T? Yeah, just the T. All right. You guys know your order of operation is. Oh yeah, guys, what's 3 squared? 9. What's 1/2 of 10? What's 5 times 9? 45. Okay, so the number is 45. Now there's one more thing: the units. Guys, what is meters per second squared multiplied by seconds squared? How do you measure distance? Meters. Guys, meters per second squared multiplied by multiplied by second squared. This is second squared, right? The unit also gets squared, right? Oh, look at that, it's meters. Oh yeah, right. So go to the edge of any cliff on Earth, drop a rock or a ball, let it fall for 3 seconds. It will have fallen that far, right? Hey, what if it's a really big boulder? What if it's like 100 times the mass and you push that off the edge? Is that going to go further or not as far, or the same distance? Same distance, because mass doesn't matter. Right? That's the Galileo scenario, isn't it? Right. I have one more. Okay, so here. I got one more question for you guys, and here's a little checklist. There's a reason I chose these 3 questions. The first question was this equation. The second this formula. I guess you make an equation with the formula, right? The second question was this expression up here. What kind of question do you think I picked for the third question? Do you think it might have something to do with this guy right here? I think it might. Give you guys a little hint. All right. So here's the question: if the cliff is 80 meters tall, how fast is it crash landing? You put that up again. These right here. All right. So the cliff is 80 meters tall. 80-meter tall cliff. 80-meter tall cliff. Right. How fast is it crash landing? Wait, you got the answer? How fast? Oh, Neil got 40 meters per second. All right. How'd you get 40 meters per second? Yep. Boom. Exactly. Let's do that. All right. So what I told you guys yesterday is this third one. Notice how it doesn't mention time and it doesn't ask for time. Right now, time is ticking in the background, of course, but this is like the time independent expression, right? Yeah. Listen. So this is not the only way to solve it, but definitely the fastest way to solve it. Let's do it. So final velocity, which we're solving for squared, is equal to initial velocity squared plus 2 times the acceleration times the distance. You could call a lowercase g, you could call x h if you want to for height, or y for like a vertical change, and just different ways to represent these characters, right? Okay. Oh, what is it? What is initial velocity again? 0 meters per second. So it just goes away, whatever. Right. So the final velocity squared is 2 times 10 meters per second squared times 80 meters drop height. Okay. Let's see. That's 800 times 2 is 1600. Guys, what's the square root of 1600? 40. And also the square root units. Meters squared per second squared. Take the square root. That gives you meters per second. Ooh. Right? You guys see that? Are we good? Right. Okay. So this is the crash speed as a function of the height of the cliff. I mean, which was the question. Right? Oh yeah.
How did you get meters per second?
You're right. You're right. Because if I multiply meters per second squared by meters, that does look like meters squared per second squared. Actually, I skipped a step from here to here because you have to do what to both sides to isolate the v. Square root, and the units also get square rooted, which leads you to meters per second. Yeah, good catch. Good catch. Right, you guys get there? Okay. Hey, could you have solved this a different way? Could you have started with this middle expression? Here, watch this. Let's go on a different path through the forest. Right. And solve for the fall time, right? Because, or wait a minute, never mind. Sorry, start with the first one. That's what I meant. Right. So you know it was falling 40 meters. You could solve for t that way. That's what you could do, right? Guys, what's 40 times 2? Hold on. I'm so sorry. I said 80. Sorry, I messed that up. I'm getting ahead of myself. 80 meters. 80 meters was the cliff height, right? Guys, what's 80 times 2? That's what I meant. What's 80 times 2? 160. What's 160 divided by this 10? 16. What's the square root of that? 4. So it's falling for 4 seconds to get to the bottom, right? Okay, now if you jump to the second guy and get the crash speed from that point of view, what is 10 meters per second squared times 4 seconds? 40 meters per second, which is the same thing we got using that third expression, right? Right, you guys see that? It's like different paths through the forest, gives you the same answer. All right, guys good? All right, so there's our warm up. All right, you guys good so far? Any question? All right, let's pull out some posters, do a little review, and then transition over to some of those pages that I gave you guys. All right, so yesterday in your notes, I had you guys draw displacement, velocity, and acceleration graphs, all versus time, for a car driving at constant velocity. This is what you guys put in your notes, right? You said, well, constant velocity means the speedometer needles just staying the same, regardless of how much time you've been driving for. It looks like this. Okay? Now, guys, what is the slope? What is the rate change of velocity equal to what physical property? It is 0. Meters per second squared, that describes an acceleration. Oh, that's why the acceleration is 0, because it's constant velocity. What if the car's going really fast? Is it still constant velocity? Still 0 acceleration? Yeah, doesn't matter how fast the car's going. Right? You could have a slow speed down here, you could have a fast speed up here, but if it's constant, then this acceleration is always 0, right? And a lot of you guys also caught on yesterday that constant velocity means you're picking up equal distance with equal time, which makes the x versus t look like a linear shape. Okay? In fact, guys, what's the slope of x versus t? It represents the what of the car? Yeah, the velocity of the car, right? Like I said, because it's like the rate that you're picking up location, right? This is the same equation here, just 3 different ways, right? You could say distance equals speed times time, right? You could say your speed is distance over time, and if you like, you can calculate the time of the trip if you know how far you have to go and how fast you're getting there, right? Okay, you guys get there? All right. Now that's a 0 acceleration environment, right? Which there's only this one expression, those 3 ways you can go with that. Okay, so that's pretty straightforward, right? Then we introduce the idea of acceleration, which is something to do with like a rate change in your velocity. I'm telling you guys right now, we're only interested in this linear acceleration, this top version. Right? So like if you're changing your speed but in a linear sense, okay? A few weeks from now, we'll worry about the steering wheel, but we don't care about the steering wheel yet, okay? So you guys get that? The rate change of your velocity is your acceleration. But you can rearrange this expression and get that second kinematic formula right here. You can do that, right? It's just a couple algebra steps away, right? All right. Then here's a cool trick to pick out. If you can identify any 3 of these 5 variables that we're juggling, we're only juggling these 5 variables, right? If you can identify any 3, then it becomes a solvable problem. Then you can figure out everything about the kinematic motion. This is always assuming uniform acceleration, right? Right. So we derive these from your lab. Well, we really derived the first 2. And if you're really curious, maybe you did the system of equations that I told you guys. You can substitute out the time and come up with the third expression, right? But we just ran that today also, right? Now this is like the version with the training wheels on it because it's got the units underneath. I got meters here. I got meters per second times seconds is meters here. This comes out to some number of meters here, right? Guys, can you only ever add meters to meters? Like for example, what is 4 meters plus 3 gallons? What is that? What is 4 meters plus 3 gallons? Is that a nonsensical question? Yeah, right. Are you allowed to add and subtract different kinds of units? No, right. So I got meters plus meters makes meters. Meters per second plus this comes out to meters per second, right? Meters per second squared times seconds is meters per second, right? You guys see that, right? So that's a common thing to look for, especially as we go down the line in physics, we get all kinds of new variables. Just make sure whatever you're adding or subtracting, right, has the same kind of unit, right? Right. So here's the version without the training wheels, right? Okay, you guys get that? All right, this next one. Yeah, a couple papers for this. Here we go. Hey, look, we're back to dropping the ball off a cliff, just like your guys' starter question. Just like yesterday, I think we did something, right? Now, this is really like a speeded up version of your guys' car and incline lab. The car and incline lab was like a slowed down version of this, right? So you guys have this 4-column table, right? How much time is ticked in seconds? What's the acceleration meters per second squared? What's the, the speed of the ball, right? And how far has it fallen in meters, right? You guys see that? Right. Now, possibly good for your notes, or you guys know I posted this to Google Classroom. All these posters I posted to Google Classroom. Might not hurt to print them out. Right. All right, so let's take off some time. Time 0, 1, 2, 3, 4, 5, 6. Time 0, you're just letting go of the ball. You're just letting go of it, right? And then every second, you're seeing what's going on with this ball. You guys got that? Right. Oh, look, I took some pictures. At time 0, he's just letting go of the ball right here. And then after 1 second, maybe it fell this far. And then 2 seconds, 3, 4, 5. Ooh, look how it's like spreading out. See how every successive second, it goes further than the previous second? In fact, if you graphed how far it fell as a function of time, it would make a what shape starts with a peak? Parabola. You guys know that from your lab, right? Is that true? All right. So this next column here, okay, just as you're letting go of the ball, let's say the ball's not in your hand, right? You just let it go like a millisecond ago. Maybe this would be a 0.001 seconds. Okay, right? Guys, what is the acceleration of the ball right at that moment? 10 meters per second squared. 10 meters per second squared. You guys like that? All right, winner. Right. How about after it's been falling for a second? Now what's the acceleration? 10 meters per second squared. Oh man, I can't trick you guys. But what about after 3 seconds? 10 meters per second squared. Oh dang. All right. Or wait, did I say 2 seconds? Or okay, after the 3rd second, is it just a constant 10 meters per second squared? Right? Now you guys know we're ignoring air drag, of course, right? Ignoring air drag. So assuming a vacuum, that would be true, right? Maybe like 9.8, but 10's a nice round number, right? Okay. All right, everybody good so far? Okay. All right. How about let's do some velocity values. Velocity, right, speed values right here. Now, right as you're letting go of the ball, how fast is it moving? 0 meters per second. Good call. So 0, and then the units meters per second. Hey, this looks like your guys' lab table. Look, variable unit, variable unit, variable unit, right? Your car and incline is just slowed down versions of this, basically, right? After 1 second, how fast does it pick up to? 10 meters per second. Okay. Which of these 3 kinematic formulas could lead you to that outcome? First, second, or third? Definitely second one, right? How fast is it picked up to? The fact that you dropped it, this number 0, you got 10 meters per second squared times 1 second gives you 10 meters per second, right? Right. Oh, you're right. 10. Swap this right here. Okay. But after the next second, after 2 seconds, how fast is it going? 20. 20 meters per second? After 3 seconds? 30? Do you guys see the pattern? Right? You guys see the pattern, right? Okay. Now this one starts at 0 because we just dropped it, so that's 0, right? But it's just A times T or G times T, right? That was also a Paul Hewitt video, right? So every second is going 10 meters per second faster than the previous second. And that's what 10 meters per second squared is, right? See how it's like you just keep adding these 10s up, right? Did I tell you guys what that process is called and what the calculus term is? If you're like accumulating this and just keep adding. Winner, integration. All right.
I win.
Yeah. So it's gonna finish like that, right? If the cliff is if it takes 5 seconds to hit the ground, then it'll be slammed at 50 meters per second. Okay. All right. You guys ready for the tough one? Tough one? Ooh, are you though? How far has it fallen in meters? That's what displacement in meter. Yeah, good call. Let's call the top of the cliff 0.0. I usually do. Now, sometimes AP does and sometimes it doesn't. Could I do this? Could I call the top of the cliff any point? Could I put really any number in that box? Yeah, technically you can. But the change after that is going to be whatever it is, right? Sometimes AP likes to call the top of the cliff like whatever height it is, and then go by elevation and call like acceleration some negative number, like gravity's pulling down. You can call, guys, could you call acceleration negative 10 meters per second all the way down? Or sorry, negative 10 meters per second squared? You could. You could define the top of the cliff to be some huge number, and then it goes down to 0 here. You can do that too. But yeah, how I usually do it is call the top of the cliff 0.0 and just give it some positive change after that, which is all we're doing here. Right. All right. I'm just prepping you guys to be able to field different perspectives on this. All right. So, all right. I'm wondering who's actually going to get this next one. Right. How far did it fall after 1 second? 5 meters. Oh, but that always tricks everybody. But not you guys. I got a sharp class this year. How'd you know it was only 5 meters? Yeah. Usually students say 10 meters and then say, no, it's 5 meters. Like, where? But you guys are on. Because which formula would you guys use? First, second, or third? Yeah, definitely the first one. Because I'm saying after some time, so if you know the time, that definitely narrows it down to one of these two. Right? And if I want to say how far, well, the second one has nothing to do with how far, but the first one does. It's definitely this guy here. Right? If you release it from rest, this term just goes to 0 anyway, whatever. Right? So let's run the numbers. Guys, what's 1 squared? 1. What's half of 10? 5. All right, and then this will come out to the units of meters to represent this meters. 5 meters. You guys got 5 meters? All right, 5 meters. How about after 2 seconds? How far did it fall in meters? 20. 20? Okay, 1/2 GT squared. Here, let me write that down. So x is 1/2 GT squared. Hey, that's the college equation. I guess this whole column could be the college equation, couldn't it? Right? We got 1/2 times 10 meters per second squared. Don't forget these have units on them. We're letting it fall for 2 seconds. Square that. Guys, what's 2 squared? 4. Half 10 is 5. What's 4 times 5? 20. And what's the unit? Meters. Oh yeah, 20 meters. Look at there. Right. It's a coincidence that both these numbers are 20. These numbers have different units, right? Meters per second, meters, different concepts. Okay. How about after 3 seconds? How far?
45.
45. Let's check this out. All right. So x is 1/2 GT squared. What's 3 squared? 9 times 5 is about 45 meters. Oh yeah, oh yeah. How about after 4 seconds? 80? So 1/2 GT squared. It's the same college formula, right? Right. How about there's an old mine shaft. Drop a rock. 5 seconds it took to hit the ground. 5 seconds. Well, how deep is it? About 125 meters. How'd you know that? College. That's the right answer. College. All right. College. Yeah. You guys be doing college? All right, you guys good on those? Good on those? All right. Let's see. What's the next one? Okay. I did have you guys make the graphs for the scenario. Guys, look at the next poster. Is it the exact same scenario, the next poster? Right, but this one's the table. You guys remember what the graphs look like? And they're in your notes from yesterday. You guys remember making these graphs? Yeah. Right. X versus t. What shape is that? A parabola, which follows 1/2 GT squared. That's a parabola, right? Just like it was in your lab. B versus t. What kind of relationship is that? Linear. And A versus t is a constant because it was like 10 meters per second squared constant, right? Right. And remember the relationships between these. So the instantaneous rate change, you can go from x to v and v to a. And if you accumulate the area under the curve called integration, you go from a to v and then v to x. Right? Guys remember that? Right. Oh, look at this. Like the slope of v is constant, v versus t, which is 10 meters per second squared. That's why this coordinate's constant, 10 meters per second squared. Right. Right. What about going from x to v? If you hold let's say your pencil or a ruler flush to the curve, if the vertex of the parabola is down here, see how this has zero slope at the bottom, and then it starts to get some slope, and then see how I'm holding the roller flush to that parabola, and the slope is going up, 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 up. You guys see that? It's getting steeper, 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 right? But that's happening at a constant rate. That's why the velocity is going up at a constant rate. Okay. Right, guys got that? All right. Oh, ooh, next one. All right, I got a challenge question for you guys. Challenge question. Challenge question. We're gonna go back to the edge of the cliff, and now we're gonna throw the ball. You guys ready to throw the ball? I can throw it upward. I can throw it downward. Let's start with throwing the ball upward. Hey guys, we've been defining down as the positive direction because gravity pulls down, the ball's going to move down. Let's go ahead and stick to that convention, right? Which means if you throw it upward, which linear direction are you throwing it? Positive or negative? Negative, right? Right. If you define down as positive, wouldn't up have to be negative, right? Would it be okay to swap those definitional directions if you wanted to?
Yes.
Yeah, you could, but we're just gonna go ahead and stick to this convention, right? Right. So let's make let's make 3 graphs. We're doing x versus t, b versus t, a versus t. You guys got your notes out? Right. Well, you can see the vertical axis on each one of those, but you know those are all versus time because that's what it's been all along, right? Right. So I want you guys to draw those 3 graphs in your notes. Draw those 3 graphs: x versus t, b versus t, a versus t. For that scenario, you're going to take the ball. Let's call the top of the cliff point 0, just like we've been knowing all along. Right. So start. But you can kind of here. So 0, 0 is going to be a point. 0, 0 is going to be a point on your x versus t graph. Right. You take the ball and you chuck it straight upwards.
Wait, so are you throwing from the bottom of the cliff?
You're at the top of the cliff. Yeah. So you're at the top of the cliff. Right? Looking down, it's a long way down. Maybe it's a 125-meter tall cliff or something. Right? Right. Take the ball and throw it straight upwards. And then when it's coming back down, it's gonna miss the cliff edge and go ahead and fall down the cliff edge.
Oh, wait, but you said up is negative.
Right. Up is the negative direction. I wonder if you guys can figure out what those graphs are going to look like, since you know you're initially throwing it in the negative direction, right? Because gravity's pulling down, we're going to call it positive. If you're throwing it up, that's negative. All right. Okay. Walking around the classroom, looks like you guys got your axes just set up right now in your notes. Oh, yeah? All right. Let's find out. Oh, all right. Joey's the winner on the first one.
Oh, yeah.
Huh? Got all 3. Oh, all right. All right. All right. Zach got all 3. Ooh, all right. Gavin got them. See, Jacob's getting them right. Oh, yeah. All right. Jensen's got them, looks like, I think. All right. Pratyush's got it. Rosa's got it. Oh, yeah. Matthew's got it. Ian's got it. Oh, okay. You guys are winning. All right. I'm getting too many winners. Too many winners. There's too much winning in this class. We gotta move on here. All right. So, let me just go ahead and reveal all 3 going on. All right. Let's look at this. All right. Oh, there's the picture for it, right? You're gonna take the ball and throw it straight upwards. It's gonna eventually peak and come back down, isn't it? Right? Remember, down is positive, up is negative. We're calling. Okay. Now, if you do that, like yesterday, I usually like to start with b versus t and then explain from there. So if you threw it into negative territory, that means as it's leaving your hand, it's going really fast negative. You guys see how initial velocity is in the negative territory, right? Now, eventually, it's going to peak and then come back down. So guys, at the moment that it peaks, what is this instantaneous speed equal to? 0 meters per second. So somewhere on the graph, see how it's to cross the time axis, like right here, at 0 meters per second, right? Hey, wouldn't that also correspond to its maximum height? Right? It's zero speed is also the point that's maximum height. It's the same time, right? So x versus t is a parabola shape, and you guys see how the parabola, like the maximum height would be like as far as it goes to the negative territory in terms of meters, right? See how that exactly lines up with that 0 velocity? Right, you guys see that? I know a lot of you guys are in calculus. One set of problems you're eventually going to do some number of months from now is like optimization problems. And so optimization, you're usually trying to maximize or minimize something. And the way that you maximize or minimize something in calculus is your calculus teacher is going to show you how to take a rate change, like find the rate change of something called derivative, right? And if you set that rate change equal to 0, you guys see how velocity is equal to 0. That corresponds to, in this case, the maximum height. You guys see that? Right? Right. If you're not in calculus, don't worry. You'll be fine this class. Okay. But hey, guys, the entire time, like as soon as the ball leaves your hand, it's traveling upward and eventually heads back downward. The entire time, is it in free fall? Yeah. It's as soon as it leaves your hand, it's in free fall. Free fall just means there's only one force acting on it, which is its own weight, right? So is it always, guys, when it's moving upward, is it still accelerating down? Is gravity still pulling down? Yeah. When it's moving down, is gravity still pulling down? Yeah. So if you look at acceleration versus time, if you only knew acceleration versus time, would you ever know which direction it was traveling? No. Would you know what time it peaked? No, you would have no idea because it's just free fall gravity the entire way, right? Right, you guys see that? All right. Any questions about that one? Are you guys ready for throw a ball downward? Throw a ball downward? All right. Go ahead and set up some axes. I'm gonna walk around and find some winners. Throw a ball downward. All right, so we're at the edge of the cliff, looking straight down. You're just gonna chuck that ball straight down. I don't know what those graphs look like. Call the top of the cliff 0.0 again, just like we've been doing all along. So 0, 0 will be one of your points on your x versus t graph. Oh, let me get the axis started, right? Get the axis started here. Okay. You guys started off right. Yeah, to throw the ball downward. Throwing the ball downward. Let's find some winners here. All right. Got Terry and Alyssa off to a good start. Got all right. Neil's got it figured out. Looks like Jacob's got it figured out. Oh, you know what? I think a lot of you guys got this figured out. Yeah. Okay. I got winners all over the place. All right. Let's go ahead and look through here. Okay. So here, I'm just gonna reveal all three, and then we'll make sense of these. Okay. Here we go. So let's look at V versus T. I usually like to start with that one and then branch out. Right, V versus T. Guys, if gravity's pulling down and we're calling it positive direction, and you also throw it downwards, aren't you throwing it into positive territory? Which means this ball is in your hand, it already has a positive velocity, right? Right. See a positive intercept here on V versus T. Okay. Now, guys, after it leaves your hand, it's moving really fast. Is it still accelerating at 10 meters per second squared? But it's moving really fast. Is that true? Yeah. Still, guys, once it leaves your hand, it's in free fall. It is accelerating at 10 meters per second squared. For example, if you throw it at 30 meters per second straight down, which is really fast, but let's just go with it. You throw it at 30 meters per second straight down. How fast is it moving after 1 second of falling? 40 meters per second, right? Because it's still picking up 10 meters per second per passing second, right? Is that slope right there and that slope right there? Are these two slopes the same slope? Yeah. And what is that slope equal to? 10 meters per second squared, right? Guys got that? Right. In fact, are these two acceleration graphs exactly identical? They are. These two acceleration graphs are exactly identical. In fact, if all you had was acceleration versus time, you wouldn't know if you dropped the ball, threw it upwards, threw it downwards. It would be ambiguous, wouldn't it? Right? All right. Now let's look at x versus t. Ooh, looks kind of curvy. Guys, is this a piece of a parabola? Right here, is this a piece of a parabola? Hey, is this right here the same piece of parabola that, like, if I go back to this other one and just chop it off right here, I just copy paste that right there? That is what that is. Right? But is that right? Is that point at 0, 0? Is that the vertex of the parabola? You're right, it is not, right? Because it looks like leaving your hand, there's a slope here. And what does the slope represent? Meters per second, rise over run, meters per second. What does that represent? the initial velocity, like how fast you threw it. Ah, look at that. Right, you guys see that? You guys navigate that? All right, are we good? All right, let's take this one right here and blow it up. Is that okay? I'm gonna take this one and blow it up. All right, boom. Well, I mean, like make it big. Yeah, in a very expressive way. All right. Hey, this was in your notes yesterday. You guys remember that? So remember the area under the curve of v versus t tells you displacement. Right, so the graph of this line could be your second kinematic expression. Vf, the final velocity it picks up to at the end of an interval is the initial velocity plus at. That looks like y equals mx plus b, right? And the area under the curve represents how far it went, which in this case is v naught t plus f at squared, which is exactly one of your kinematic equations. It's that first one, isn't it? First kinematic expression, right? So these two kinematic expressions are embedded in that graph, right? The actual line itself and the area under the curve, right? So, all right. I got some more posters, but let's flip over to these puzzles right here. All right. I'm gonna just start with the bonus page. So remember, you guys remember this page? Now this is bonus. I think it's good practice. If you do them all and you turn them in, then I'll throw you guys some points in the butt. Right? But if you don't, it's just bonus. Okay. All right. All right. So let's do. What do we do here? Let's do number 5 and 6. Start out. Let's do 5 and 6. Right now, there are lots of different versions of this paper floating around. So all of us have the same scenario in number 5 and 6, but all of us have different numbers. Is that okay? All of us have different numbers. Right. Right, so this one says a ball is dropped from a tree house and it reaches the ground in some given time. Okay, so looks like I went with 9.8 meters per second squared on this one. Somebody brought a stopwatch to this party, and it took this interval of time to reach the ground. Right? You know what? I should not have explicitly given you this number, but the fact that it says dropped, the fact that it says dropped, you would know initial velocity is 0 anyway, right? Right? Okay. So there's a pair of questions, and the two questions are the two kinematic variables that I didn't give you, right? So how far did it fall, and also what's the crash speed, right? You know, there's different ways you can navigate these kinematic expressions to get to the answer, right? But what's one that you want to start with? What do you guys think? You can solve both these questions in any order you want. The second one, second kinematic expression, right? Now, if you do that one, you're saying how fast is it crashing as a function of the fall time. Yeah, we can solve that. We can solve that. Let's do that. Now that would be question number 6. Okay, question number 6. The speed it picks up to is the speed it started with, or I should say velocity, right? Plus, you could say AT or you could say GT. Either of those would be great, right? So the fact that you dropped it means this is 0 meters per second. So the velocity it picks up to is, well, we got 9.8 meters per second squared I used on this page. And my fall time says 0.7 seconds. Now careful, because it may or may not say that on your page. In fact, it probably doesn't. Okay. Right. Okay. So we all have an earth tree. Well, I guess that's the only kind of trees there are, and at least that we know of. And probably all have a different fall time. Okay. So what's that times that? Right. I'm getting a crash speed of this many meters per second, which is really too many digits of precision, but I can get the answer from that, right? You guys see an answer choice that, right? And the other question, number 5, says how far did it fall? Now you have some options. The fact that you know the crash speed opens up the third kinematic expression as a possibility, because you can solve for crash speed as a function of, wait a minute, what did it say? What are we solving for? How far did it fall? Okay, yeah, you could do that. Or you could just do the first one. First or third, you guys see that? Let's just go ahead and do the first one, right? Because that's, we can just solve this with the college equation. The height of the tree is just very simply 1/2 AT squared. All right. Take a split. If I don't see you tomorrow, then this could be a pretty good practice page to work on, right? Or those college physics questions. Yeah, guys, if you finish your lab write-up with those 3 parts, then go ahead and turn that to the grade tray. I'm looking for a lab table, 6 graphs, and your write-up that you scored out of 12 with the colored pencil. Right. If you don't have all those parts, then you can turn it in next time I see you in school. All right. I hope to see you guys tomorrow. If not, happy hurricaning.